Hello, everyone. Welcome. Thank you for joining us. My name is Corey. I work on the OpenSpace project at the American Museum of Natural History. We're very excited to be bringing you this live stream about the James Webb Space Telescope in partnership with StarNet's NASA at My Library and Embry Riddle Aeronautical University. Here with me today are two of my colleagues, Dr. Jackie Faherty and Micah Echnapura. Hi.
Hi.
Hi, Corey. Hi, Micah.
And also with us here today in the YouTube chat and Facebook comments, we have Marina Gemma, who is a planetary scientist at the American Museum of Natural History, and Megan Platt, who's a junior in astronomy at Embry Riddle Aeronautical University. So they're going to be answering some of your questions, so be sure to put them in there. And without further ado, I'm going to hand it off to Jackie and Micah, and we're going to dive right in.
Thanks, Corey. So I'll get us started with a little bit of background, as Micah is going to be kind of flying us around in this software called OpenSpace. It's a NASA-funded software that we are co-developing at the American Museum of Natural History with several amazing partners. And before we get into the visual aspects of this, and you're seeing James Webb there, I wanted to set this up for you because today's actually a really cool day. This telescope, the James Webb Space Telescope, arrived today in French Guiana, which is where it is going to be launching from to head into space. So today, as we're giving you this program, is a really fun and exciting day because it is at its final destination on Earth as it's getting ready to launch. And the other setup for this is this telescope has been in the making since 1989. So some of you on this call may even have been born before 1989 or after. I'm assuming we got some young ones. So this may have been planned your whole lives, and it is going to launch on December 18th. So we're going to take you through launch, to the science of it, to what it's going to look at. And for the launch part of it, I'm going to hand it over to Micah, who's going to explain to you exactly what's going to be happening on December 18th when this telescope gets launched from French Guiana. So Micah, why don't you take us through what the launch is going to look like and the deployment of the telescope?
For sure. Thanks, Jackie. And so what we're looking at right now is actually the telescope folded up. And this would be after it's already launched off of Earth. And it's going to be doing the first part of its unfolding here. And so what we're seeing right now in real time is the first part of the solar panel unfolding. And then all of a sudden you see we blast away from Earth. Now we're going at 2 hours per second as the telescope travels away from Earth, and it has to actually go a lot farther away before it can start doing the other phases of its deployment. It's actually going to take a while to go out and to reach its location where it wants to go before it can start unfolding and do the certain parts. So what we're actually seeing right now is the sun shield palette, and these on either side of the telescope there is a sun shield, and this is aside from the mirror perhaps the most important part of the telescope. And what this is this is the part of the telescope that is going to be blocking the sun and going to be protecting the mirror from the heat of the sun. And so these parts that you just saw unfold will always be facing the sun and protecting the telescope. And so as we travel out, we are already a couple days past the launch, and you can see this trail behind us. That's actually the trail of the moon going around the Earth, this red line that you see with the Earth in the center. And so you could see that by now we've actually traveled farther away from Earth than the moon is, but in total we're going to travel 4 times the distance to a distance of almost 1 million miles away. So
Micah, just an aside in here, as you're watching this, we're giving you a fast-forwarded version of the deployment of the telescope. This is the most complex instrument that we have ever sent into space, and it is going to deploy on its own. No people are going to be near it. It's very, very stressful to consider all of these moving parts. And now you're getting the sunshade fully deploying here, right, Micah? It's
Yeah.
fully so stressful to watch this.
So there you're seeing the membrane of the sun shield unfold. And what we actually, as we saw it unfold, we were actually running our simulation at 30 minutes a second. So that unfolding of the sun shield that happened really fast for us was actually 1,800 times as fast as it normally would happen. So when we say it's going to take a long time for these stages to happen, it really does mean a long time. And that's why we sped it up, because this would be a pretty long program if we had to wait to watch the whole thing.
And
What you're
that's
seeing,
secondary, right? Yep.
yeah, so this is the secondary mirror unfolding and deploying. And what you can see after the secondary mirror unfolds, then portions of the primary mirror unfolding. So if we look at it, we see the primary mirror is the big gold pieces in the back, and the secondary mirror is the part sticking out in the front, and that focuses the light into the primary mirror. Still on the side, and actually the first ones unfolding right now, are the wings of the primary mirror. So the mirror is so big, you can actually see it's built in these hexagon panels. And it was so big that they had to fold up some of the panels for when it was launching. And then they're some of the last pieces that actually unfold. And by now the telescope is ready.
And one thing that's important for people to understand about this is that what you just saw was an extremely complicated object with moving parts. And one thing I'd like to instill in you is that part of why James Webb is so stressful to consider is because every single one of the moving parts is a position for failure for the telescope. Because if one of those moving parts breaks, has a problem, whatnot, then we can't get done with the rest of the sequence. So the moving parts should have struck you. You might have thought, oh, it doesn't look so bad. But that was a lot of moving parts. And that is part of the beauty and the accomplishment that we will all be celebrating after the 30-day time that it takes to get to that point. So 30 days, right, Micah, to get to this point?
Yeah. And then 30 days to get to this point, but we will still be running a lot of tests on the telescope and stuff once it gets to this point. So just because you heard 30 days doesn't mean that I think we're going to get to use it right away after 30 days.
Right. No, that's when the excitement begins and they start testing all of the suite of instruments that are on board the James Webb Space Telescope. It has several. So they'll have to start testing. They're going to check to make sure it's communicating properly back to Earth. So there's a lot that goes on. Oh, hello.
Hi, I had a great related question that I wanted to pop in, if you wouldn't mind. And it was pre-submitted by Karen at the New Brunswick Free Public Library. And she was asking, how long will it take to see the first images once the telescope is in place?
That is a great question, Karen. And so I will say that so it'll get to the point where it can start testing operations when 30 days go by and it's fully unfurled. And then after that, they do a series of tests. Some of those tests might yield images, but you can really bank on science operations beginning about 6 months after the telescope is unfurled. So it's likely that an image will come out before those 6 months are up, so before June of 2022. But that's the time that you can start to expect to see some of these amazing images of what we have decided we will be pointing that telescope to in the beginning. But great question. So keep your eye on some calendar items. So 6 months after, you're going to start to see lots of images coming up. And you might get some initial images before that.
Amazing. Thank you.
All right, continuing on. Micah, where are we at in the launch now?
So now we are actually almost to the point of where JWST is looking to go. And that's the L2 Lagrange point.
Yeah, so a special aspect of the James Webb Space Telescope is that it is not being launched close to Earth. As Micah has said, we're pretty far from Earth right now. The Lagrange point number 2 here is about 1 million miles away from Earth. You might be saying, what the heck is an L2? And there's also an L1 there. So what these are positions in space that are a consequence of the gravitational interaction between the Earth, the Sun, and the Moon. And there are 5 points that are oriented around the Earth, Sun, Moon system that are invisible points. There's nothing there. It's not like a body or something that's there. There's no celestial object there, but they are points of stability, gravitational stability in the system, so that you can arrive at this point of L2. It's abbreviated L2, but it's actually named after a very famous physicist named Lagrange. And he was the one that determined that these positions existed. And L2 is about 1 million miles away. We know that you can launch things there and they can remain stable as you orbit this invisible point. And you don't have to use much fuel to do it, because that's really important. Remember, when JWST launches, it's gone. It's gone from us, and we don't get to see it again, because it will be out 1 million miles away, and we can't refuel it. We can't repair it. It's just going to be out here. And I think you're going to run time, right, Micah, so we can see what that orbit looks like?
Yeah.
And once you do it, so we'll be able to see what the orbit looks like as you're going. The other thing that we get asked a lot, and you might be wondering, is why are we so far away? Why? The Hubble Space Telescope, as you know, is very close to the Earth. It is just a couple hundred miles above your head. So depending on where you guys are, I can see in the chat, you've got somebody from Wisconsin, maybe somebody from, I see Wisconsin here I see somebody from Brazil. You guys are much farther away from us in New York than the Hubble Space Telescope is from you right now. And it is close by, and it can operate there because it can handle the heat from the Earth and the Moon. But the James Webb Space Telescope is operating at a wavelength that requires it to be extremely cold. And the coldness is why it is so far away from the Earth. The Earth and the Moon provide too much heat nearby, and so it wouldn't be able to have the optimal operation that we want this kind of telescope to have if it was close to Earth. So it hangs out here at Lagrange point number 2, 1 million miles away, in this nice cold spot. And Micah's kind of running time here.
Yeah, we're actually going at 1 day per second right here.
1 day per second.
Yeah.
And you can really tell by the moon, right, Micah?
Yeah, because you can actually see in about 30 seconds, the moon will go once around the Earth.
And it's showing you this saddle-like orbit that the James Webb Space Telescope is on as it stably orbits Lagrange point number 2. It will remain here for the duration of the whole of this mission, which will hopefully be much longer than the promised just several years of the mission, maybe 5 to 10 years of a mission. All right, so that is the orbit of the telescope. Now what we want to talk about is the kind of light that the James Webb Space Telescope is going to look at and how this telescope is going to operate. So in comparison to the Hubble Space Telescope, which has operated for over 27 years or so, it has been operating primarily at wavelengths that you guys should feel comfortable with, at visible wavelengths. The same wavelengths that your eye detects is what Hubble primarily operates in. It also has some ultraviolet light that it operates in and a bit of near infrared light. But for the most part, when you think of Hubble, you should think of an optical observatory. James Webb is an infrared observatory. Now here's the nighttime sky that Micah has brought up here, and we're orienting you so that you're kind of looking. The James Webb is brought back in here, so you're seeing this gorgeous view of the Milky Way, which you might catch if you could get yourself to a really dark sky somewhere where you don't have a lot of light pollution, your eye might be able to make out some of these gorgeous stars. And look at the Milky Way. I'm going to explain to you why James Webb is a different kind of observatory than Hubble. So this might be an image that Hubble might take, a gorgeous Milky Way image. But notice that as we're kind of like moving around the Milky Way here, you're seeing all these dark spots, what appears to be the absence of stars. And that is not really the absence of anything. What it is material between your eye and what's behind it that is blocking you from being able to see anything. It's the absorption of light by dust and by gas, which is prominent in the Milky Way, because what we're looking at when we see the bulk and the beauty of the bulk of the Milky Way is all of the majority of stars and all of their components. And so we are a spiral galaxy that's really thin like a pancake. And so you're looking through the bulk of the stars when you look towards this. Now let's switch to a different wavelength, like put on different eyes. And Micah has just switched it to infrared light. This is a light that James Webb is going to be optimized for. And what you can see right away was those dark spots of the Milky Way just came to life. And you see that there's color to them. And you can even see stars that are in those dark areas. This is near infrared light, light that your eye cannot see, but light that you actually radiate in. So if you were to take your hands, clap them together, rub real hard, and then bring them close to your face but not touch your face, you would be feeling this heat radiating off your hands. That heat is exactly what we are catching and mapping when we look in this wavelength. Infrared light. And you can even look at a slightly different view of it at longer wavelengths than even this band. This is actually an image from the 2-micron all-sky survey, which was a NASA mission. And now Micah has brought up an even longer wavelength. Our body doesn't radiate in this wavelength. And this one is now the wide field infrared explorer light. And notice this gorgeous, stunning views of structure within those areas that were in the visible, were basically dark areas where we couldn't see anything. And now all of a sudden what's come to life are shells. You can see what appears to be pockets of structure, and much of what you're seeing actually is star formation. So as we're kind of moving around, you can see we're going to actually come around to, I think, Orion as we're moving, Micah. And one of the things that we also were going to show you is how astronomers map the sky. So as Micah kind of brings us over just a little, you can see just below what the plane of the Milky Way is more of this amazing structure. Young stars being formed. The reason you can see them really well at this wavelength, which is the optimal wavelengths for James Webb, is because they are glowing in dust. Dust. James Webb is going to give you a lot of imaging of dust. The structure of the dust is how you might think of James Webb after today. So this is the context of where James Webb will be looking. Now you might say, okay, well, you have these images. Don't we know what's there? What does James Webb bring on top of this? Well, this shows you the wavelengths that it'll be good at. But then on top of that, it's a singular telescope with phenomenal spatial resolution. So it's going to be able to really get in there and show you the details of the images of these objects. And it has several instruments on board that's going to give us insights into the composition, detailed compositions. Now, Micah has brought up for us the constellation lines. So this is showing you your nighttime sky boundary. This is the stick figures of it. And we have another map that's going to show you actual boundaries. And as an astronomer, I think of the nighttime sky this way. And Micah, this surprised you, didn't it? That this is actually how we map the sky?
Yeah, I always wondered how come the astronomers are always talking about the constellations, and I thought that, they just kind of talked about them for history. But then when I saw this version with the red borders, I realized that, oh, they're using the constellations like a map, I like to think of this as I'm looking at a map of the globe and each constellation's a different country.
Yeah. And this is how we're now going to explain to you where we're going to point the James Webb Space Telescope to, because these constellations are really showing you where we're going to say we're going to now look towards Orion or to Canis Major or to Monosaurus or to Canis Minor. All of these are areas of the sky that we think of as maps of where we will be looking. And Michael, one other thing that we want to showcase. So remember, you saw James Webb. We've seen the wavelength coverage that it's going to do. You saw some of the map of how we're going to talk about the sky. Now, one other thing, Micah, do you want to show the field of view that James Webb? Okay, great. Do you want to take us through what we're looking at now?
Yeah, so we're actually seeing two different things that I just turned on. And what we're seeing is this white field of view of the telescope. So we're actually seeing, if the telescope was looking in this direction, this little point that these lines are directing to is where it would be looking right now. But then this lighter gray area that's actually covering almost the whole sky right now, but you can actually see it's a band. This is the portion of the sky that the telescope can look at on any given night and or at this given time. So you heard me earlier talking about the sun shield and how that will always be facing the sun. So in order to protect it from the sun, a specific portion always needs to be facing the sun. And as a result of that, we can only look at a certain portion of the sky on any given evening.
Right. So we're going to now switch into like a tour using that as a guide, pointing the James Webb Space Telescope as if we were the astronomers doing it right now. And before we move into that mode, I just want to ask Corey if there's any questions we want to bring in right now. Anything on the deployment or the wavelengths, actually anything at all, but specific to that aspect.
We don't have any questions about that, but we do have a good question thinking ahead to about the life of the Webb telescope. I'm going to bring that on screen now. It's from Cohen, 9 years old. How long will the James Webb telescope be in space, and how long will it be collecting data?
Oh, Cohen, that's a great question. So the answer, I think, to how long will James Webb be in space, I think the answer is basically forever. I mean, it's off and it's going to be put in an orbit where when it's done with its scientific mission, they'll have to send it off so that it doesn't interfere with anything else. But I don't think there's a plan at all to do anything else besides just like send it into a non-destructive orbit. But the operational part is probably what you want to know. How long will astronomers be able to use it? And actually, that's an intriguing question because it's going to be highly dependent on the first few moments of when they're getting it into that place of L2, because there's a certain amount of gas that it has, propellant. And they're going to use the propellant to keep it in that stable L2 orbit. They don't have to do much, but they have to use a little. And when they first get it into that position, they're going to use an amount to make sure it settles. And if they use too much, it will take away from the length of the mission. If they use an efficient amount, it'll mean we'll have a couple more years. The actual length of the mission of JWST is nominally, it's just a couple of years. I want to say it's like 5 to 10 years. I can't remember the exact number, but it's not a 25 or 30-year mission. It's a shorter mission. So we've got to pack all of our science into the first few years of having it. And that's when it will be working its best, probably, because that's going to be when it's got the fresh eyes on the sky. Great question, though.
Awesome.
Okay. How about we do a couple of tour moments? Micah, why don't we start with, now what we're going to do, we're going to take you guys to objects that James Webb is going to be looking at in its first year of operations. the first few targets that it's going to be looking at. The first one we're going to take you to, we're going to start far away and then we're going to bring you back in, is the Hubble Ultra Deep Field. And so in order to do that, Mike is going to explain too this new mode of open space that we're going to go into that allows us to zoom in. Right, Micah?
Yeah, so the first thing I'm doing is I just was going to point the telescope, and then I'm going to bring onto screen a new feature that we are building into our software here, which we are calling our Sky Browser. It's in conjunction utilizing the Worldwide Telescope software that we can actually take our model here of James Webb, point it, and then what we can do is we can actually add onto the screen, and I'll go ahead and do that now, a view of what it will be seeing and what it will be looking at. And so what we see here in this little window, which I'll make bigger for us, is a view from the Worldwide Telescope of our all sky survey. And now I can actually add in Hubble's image, and we can actually see the image that Hubble took. Very famous image.
Yeah, we're gonna have a look at what's called the Hubble Ultra Deep Field. And now what Micah was showing you beforehand is this was a patch of sky that was essentially empty. It looked like there was nothing there. And we wanted that because we wanted to be able to do something where you could turn the Hubble Space Telescope to it and just let the Hubble take a long exposure. And it basically sat on this area of the sky for about 10 days in order to image the deepest possible kind of thing we could. How many galaxies could we be getting if we took this image? And now if you zoom in, yeah, Mike is zooming in on this image. This is an astounding image that really has provided a lot of insights into galaxy evolution, what the early universe might have looked like with some of these old galaxies in here. Almost everything in this image, aside from the things with the 4 spikes there, that's actually a star. There are very, very few stars in this image, just a handful. Everything else that you're seeing is a galaxy. Galaxies at different stages of evolution, galaxies that are interacting with each other. And the ones that look orange are the farthest away ones. The farther away you get, the farther back in time you're looking at, because you are looking at the earliest galaxies. When you look back, when you look farther from us, you're looking at the light as it was when it left the time ago that it is in distance. So you can see something that's, say, 12 billion light years away. You are looking at a galaxy that is just about 1 billion years old. It's just after the Big Bang. And so what they're going to do in the first science images is they are going to take a James Webb Space Telescope deep image of this exact same field. It's going to be called W-Deep. So Hubble Ultra Deep Field, or HUD-F, is the first is this first target, and was called by Hubble. And they're going to spend about 121 hours of James Webb Space Telescope on it, and actually put a lot of instruments on this so that they can look at the chemistry in these galaxies. So we can see what was happening, especially in the reddish ones that are so old and would tell us about the first stars and how they formed. So they can inform us on exactly, so that's where the dust is. The dust is in the first stars. And we'll be able to look to that when we take this James Webb Space Telescope deep image of this field. So look out for this W-Deep image when it first comes out. It's going to be a really gorgeous image packed with science about early young, I shouldn't say young, the early universe. Okay, let's go on to our next target. We're going to move closer.
I could spend all night looking just at that picture, huh?
Right? I've spent a lot of time zooming in and out of that image. It's a gorgeous one. So, Micah, I think we should let's look at a galaxy now, because this is another major category for James Webb in looking at specific galaxies. And let's go to a galaxy that's called Messier 82 or M82. So those of you that are familiar with your nighttime sky know the Messier catalog, which is a catalog of objects that are pretty gorgeous to look at with a telescope. Some of them are very nice to look at with binoculars. And as we move over, Micah, why don't we bring the boundaries back up so we can actually see what part of the sky we're looking in M82. Because this is actually, I don't remember what area of the sky we're looking in, but if you put the boundaries up, we'll be able to see right away. I can see the constellation of Gemini there. And if you can't, no worries.
There
There we go. We'd have to have the constellation names on there too, because I don't recognize the shapes in the map. Ursa Major, right. This is in the constellation of Ursa Major. So those of us in the Northern Hemisphere, you can actually look for this object. Oh, what am I talking about? Ursa Major's to the right. That's Pegasus. Okay, so, oh no, it is Ursa Major, and I'm looking at Ursa Minor. Sorry, guys. Now I'm saying the wrong things. Ursa Major, Big Dipper, pouring into the Little Dipper. Okay, so Micah has zoomed in for us in this part of the sky that is near Ursa Major, a very easy portion of the sky for you to see in the Northern Hemisphere. And what he zoomed in on is an image of this starburst galaxy, M82. So this galaxy has an extremely large amount of star formation going on in it. It might not look like a galaxy that you're used to, and that's because it's got a lot of action going on within it. I think there's another image or so that you can show, Micah. So this image here is showcasing for you the bulk of the galaxy is kind of running from the bottom left-hand corner to the top right-hand corner. And then what's in that kind of bluish and reddish color is the X-rays that are coming from this. What drives these starburst galaxies is probably the collision between two galaxies. So M82 is either in the process of eating another galaxy, or M82 is basically the consequence of two galaxies colliding, or it might be that it just had a major interaction with another galaxy. So there's a lot of hot gas and dust, and you can really see that in the X-rays. There's a lot of energy coming from whatever this interaction was. But at the center of this, and you can kind of zoom in on it, Micah, what you have are what's called super star clusters. And therein lies these stars that are just forming. They're enshrouded in dust. And the James Webb Space Telescope is dedicating 42 hours to stare at M82, to look towards the center of it. And you kind of highlight some of the circles that you're seeing in here. Those central dots, yep, you're getting them all in there. Those are the superstar clusters that are going to be mapped spatially. So we're going to get really detailed imagery of them. And we're going to be able to discern what's the chemistry, what is happening with the dust, because those are going to generate the new stars in this galaxy and inform us about the process of how these galaxy collisions, which we know happen all the time, which is slated to happen for the Milky Way galaxy when we collide with Andromeda. We're actually eating the Large and Small Magellanic Clouds in the Sagittarius Dwarf Galaxy right now. But it will inform us about this process. So we're going to see through all of the dust that you're seeing in this image right here, and map this galaxy, this archetypical starburst galaxy, a very important prototypical galaxy for our understanding of the evolution of galaxies in the universe. This is going to be an awesome image. Are you excited about this one, Micah?
Yeah, God, as you were describing it, I'm thinking about the detail that we have already on such a far away object, and the way you described that, we're going to have so much more detail. It's almost unbelievable.
Yeah, I agree. This thing is, I want to tell you the actual, so it's 11 million light years away. 11 million light years away, and we will be mapping its star clusters. I love that that's happening.
Amazing.
Okay, let's get even a little bit closer. Now we're going to come within the galaxy, And let's go to the Crab Nebula. Some of you might actually know this object. It's also a very famous nighttime sky object. And it has a very famous story around the Crab Nebula. So great, you're moving us over. It's in the constellation of Taurus. Taurus the bull. It's up towards the top of the V of Taurus. And the deal with the Crab Nebula is that it was discovered and cataloged as far back as the year 1054, where Chinese astronomers noticed that a new star could be seen during the day. And the reason why a new star could be seen during the day is because at that time, a supernova happened. And Micah's just zoomed in on this image that we have from a combination of the Hubble Space Telescope, the Chandra X-ray Observatory, and some infrared imagery from the Spitzer Space Telescope. This image is a combination image that shows you lots of different wavelengths of light that are coming from the remnant, the blast zone from when that star went supernova. So the Crab Nebula is one of the most famous supernova remnants. At the center of the Crab Nebula there, and you kind of zoom in, there's what's called a pulsar, which is a neutron star that's rapidly rotating. And a neutron star is the remnant of what would have been probably a star about 10 times the mass of our sun, but it blew off all the majority of its material and then caved in on itself so badly that the only thing that's stopping it from collapsing further is that all of the neutrons have been packed super tight together. And it's real dense and it's real dangerous because you got about 2 times the mass of the sun all packed into a radius that's about the size of the island of Manhattan. And Micah's kind of zoomed in. That's the central area. James Webb Space Telescope is going to be taking detailed imagery as well as looking at the composition of the whole of the ring around it. So all of that structure, Micah, that you can kind of point out in there, the knots, what a lot of that is dust that was blown off from that star when it died in the supernova. And they are going to dedicate across a couple of different programs, but it's getting 23 hours of program of James Webb Space Telescope time to do a detailed mapping of the iron and the nickel that is in the dust amounts in here to see where it is, in what abundance that it is, and search for compositional variations, how it varies through this structure. And in doing that, they're going to be able to test a couple of different ideas that people have about what the progenitor was for this and how the explosion happened and how it's feeding back to the rest of the galaxy and really driving the next generation of star formation. All of that material that Micah is pointing out there, we're going to be mapping what the compositional information is on this with James Webb Space Telescope. And in the process, you are going to get a gorgeous infrared image of this nebula like you've never seen before. So get excited for the Crab Nebula. Okay, next one, since we just showed you that pulsar, and it did look like you might have noticed that it had a jet coming out of it, we're going to move to even closer to the sun, since the Crab Nebula is on the order probably of about 6,500 or so light years away. We're going to come in closer to an object called Herbig-Haro 212, or HH212. It's about 1,300 light years away, and it's going to showcase for you a different kind of object that the James Webb Space Telescope is going to look at, and that is a young star. So we started with the Hubble Ultra Deep Field, which is basically first galaxies type stuff. We moved into a starburst galaxy and looked at what it's going to map for galaxies itself, and then this supernova remnant, and now on to well within the galaxy within Orion, this young star that Micah has zoomed in on. And check this out. Look at that object. It has this massive jet that is coming off of it. If you kind of zoom in, you will see that there's actually a central star right where there's a gap in between those two bright gaps. So there is a central star in there. And what's happening is that star is in formation. It is forming. And it's got a disk around it, and it's blowing material off in both directions as a jet. And what they're going to do is point the James Webb Space Telescope at this object, stare at it for about 7 hours in order to spatially resolve what's happening at those bow shocks. So, Micah, you can even zoom in and see. Yeah, see how there's a shock? The reason why that's shaped like a bow is because that's a little explosion that's going off. And it's blowing a lot of energy that's interacting with material, with dust. Back on dust, you'll hear me say dust about 1 million times when I talk about James Webb. And it's interacting with this energy wave that's coming from that central star that's very young and being born. And we are going to map what the chemistry is and the structure is of the interaction there, of at those shocks, those knots that you're seeing. So the James Webb is going to take an image of this object in the first guaranteed time observing. This is one of the first targets that it is going to be looking at. So look out for that. All right, last two things we'll show you because we're almost at the end of the time. And I'll just pause here even to see, Corey, if there's any questions you wanted to throw in before I get to the last two objects, which are outside of Worldwide Telescope.
You know, I think a good question that we had come up here is about why it's important that we're looking at things that are from the beginning of the universe, and how does that inform our understanding today or what's occurring today?
Rhonda, great question. The idea of, why do we want to know what happened at the beginning of time, or at least what we really mean is why do we care about what happened right after the Big Bang? Because that's what we talk about when we talk about first galaxies, first light. And that's because we're trying to understand the formation and evolution of the universe. How did this come to be? Because we do want to understand the space that we live in. It all comes back to the question of life on this planet. How did it get to the point where we could even have this? And if you're going to understand that, the question will take you on a deep dive down to understanding why the universe even exists as it does. And if we want to understand why the Milky Way looks like it does today, we need to understand what it started as. And so we go back and we look at those galaxies to see what they started out as, the baby pictures, to try and figure out what we are now. And then that gives us hints as to where we're going. So there's a lot of that is involved in this. From first, this all comes down to basic questions at our core. Where did we come from? Why are we here? If you want to get at any of that, you need to go and look back in time to understand the beginning of the universe.
That's awesome. Thanks, Jackie. And just a reminder, everybody put their questions in the chat because we're going to be going up to our Q&A shortly and wrapping up the live stream. So carry on.
Okay, last things. One that I wanted to showcase for you. Michael, why don't we, if we can turn on the brown dwarf catalog, that's actually the next one that I wanted to go to. Because we're going to be done with Worldwide Telescope for now, as we're going to do the brown dwarf catalog that we have in here is there's another kind of object, and part of why I wanted to bring this one up is because I actually am an astronomer. I applied for James Webb Space Telescope time, and I got 25 hours of James Webb Space Telescope time to look at this very special kind of object. And Micah, if we could bring up the 2-micron all-sky survey as well. So the science that I do focuses on these objects that are in between stars and planets. And so they're highlighted by kind of cartoon images of them. They're cold, compact sources that give off the majority of their light in the infrared. They glow in the infrared. They do not glow invisible. You can't do much of anything with them in the visible. They were found in the infrared through that 2-micron all-sky survey image. You're looking at us now.
Sorry
And
about
when
that.
did we lose OpenSpace? If we did,
Yeah.
that's okay.
Coming right back.
So we found all of these objects with 2 mass, and what they are these objects that basically look like Jupiter. And so we have this opportunity with the James Webb Space Telescope to point James Webb at them, and I got 20 plus hours to look at 12 of them that are really, really similar to Jupiter. And I am going to study their compositions, and I'm going to map what's in their atmospheres. I'll be able to tell you what kind of clouds they have. I'll be able to tell you maybe what kinds of metallicities they have. So like how much metal is in their core composition, and be able to tell you a little bit more about the evolution of objects that are in between stars and planets. So brown dwarfs are key objects that are there's a couple of different teams that'll be looking at them. So look for that science. They won't generate the same kinds of phenomenal looking images like you might get from the Hubble Ultra Deep Field or HH212, but you will get some really good stuff. All right.
Jackie, can I just follow up and say James Webb will learn about atmospheres? I didn't know that.
Yes. Oh, definitely. That is a key thing that it's going to tell us when it comes to studying single source objects like the brown dwarfs. You are going to hear a lot about brown dwarfs with James Webb. Let me just tell all of the people watching this on this. And brown dwarfs are the amazing objects of James Webb because they glow in the infrared and they look like Jupiter, and they don't have a star that you have to block in order to get to their light. And then the last thing is that it will look at exoplanets. So we may not be able to switch back into OpenSpace, but know that that is the last kind of object that we were going to showcase for you. You'll see some brown dwarfs coming out with James Webb, and then you're going to see some exoplanets, because with the exoplanet science, you won't see images of them, but what we will be doing is taking images of the stars. Oh, great. So Michael, why don't we end by taking everybody we'll take the brown dwarfs off. And the last major target of interest for James Webb is going to be exoplanets. So why don't we bring up the exoplanet catalog, and we can take the 2-mass all-sky image down. And now what Micah has here is circled are all of the stars that have exoplanet detections around them. Every star may very well have a planet around it, but these are the stars that we have definitively detected a planet or more than one planet around. And Micah's going to fly us to a very special system called TRAPPIST that is a prime target for James Webb Space Telescope in the first few moments. TRAPPIST is a system of 7 rocky planets all packed in to an orbit less than that of Mercury around a star that's barely a star, frankly. It's much more like a brown dwarf than it is like a star. It's a super low mass star that has these 7 rocky worlds around it. And it's only about 30 light years away. So it's super close by. Micah's flown us to the system. So you can see that the star at the center here is red because it's so cold. And those are the 7 rocky worlds that are around it. And the James Webb Space Telescope is going to look at all of these planets and by looking at them, it's going to wait until the planets are in front of the star, doing what would be called like a transit of the star by the planet. It's going to take some images. It's going to take some spectra. It's going to take the light and pass it through a prism. It's going to see what's in it so that we can make some determinations about what's in the atmospheres of those planets, even if they have an atmosphere, because that's a big question. So we will be looking at these planets. So look out for these targets as main James Webb Space Telescope targets. Okay, I think we're going to end there, Corey. And if you guys have any other questions, we would love to take them. But hopefully we've gotten you excited about this telescope that arrived at its launch site today.
Yes, very exciting. I do have a short question related to exoplanets from our friends at StarNet, so I'm going to bring that up. What's the smallest exoplanet it might see? Do we know?
Well,
Wow.
I think that the TRAPPIST planets are among the, well, I shouldn't say that. There are really small planets that have been detected, and I spent a lot of time prepping for this program for you guys by reading people's James Webb Space Telescope proposals. And I don't have a handle on all of the targets. Frankly, people would try and get James Webb to stare at every exoplanet if they could. But just so everybody knows, it's highly competitive right now to win the time to convince the other astronomers to stare at your object. It's how this
Uh,
all works. You have to submit a proposal and pitch your best idea, like absolute best idea. Tell us why we turn this $10 billion telescope on your object. And it's a race for the astronomers to come up with the best ideas. And so it is definitely looking at these TRAPPIST planets, and specifically it's going to look at the C planet in very, very much detail, which is actually the second planet from the star. And that's like an Earth-sized planet, an Earth radius, an Earth mass-ish object. But if it might be looking at even smaller worlds. I'd have to read more carefully the other accepted proposals. There looked like there's about 50 different exoplanet proposals that were accepted in for the first year and a half of operations for James Webb, or thereabouts the first year and a half. I love talking about the process because I think it's not everybody understands it, and it's also super stressful to think about as an astronomer.
Yeah, absolutely.
yeah, I thought it was amazing that it's pretty much seemed to me that pretty much anybody can apply to get telescope time. That doesn't mean you'll get your application approved, but just about anyone can apply. Is that right?
Yeah, and I wanted to note that the proposal that I got accepted, 2 of the objects that are part of the 12 that I had were discovered by citizen scientists through a program that I co-founded called Backyard Worlds. So regular people that are not professional scientists, discovered objects that I got so excited about. I started a follow-up campaign on them that led me down to the trail of needing James Webb Space Telescope time for them. And of all the targets, I chose their targets to be a part of this first inaugural moment. And I think that's pretty special. That means that even if you don't lead a proposal, you can be a part of the science of the James Webb Space Telescope. There are many ways for you to get involved and to get excited.
That's great. Thank you. Thank you, Jackie. And thank you, Micah, for a great program tonight. And thank you all for joining us. I also want to put up just very quickly our chat experts who we had with us today, Megan and Marina. Thank you both so much for answering all those questions. And also thanks to our partners on this program. That's NASA at My Library and Embry Riddle Aeronautical University. So until next time, thank you.
Thanks, everybody.
Bye, everyone.
Bye, everybody.